let's first of all see, does anybody have a question? So, we were talking about path integrals, and I wanted to continue that. We've been talking about path integrals in quantum mechanics, and we've just been talking about amplitudes. But here we're going to get into something closer to field theory, namely correlation functions. Let's first of all remember that a position operator at time t is equal to e to the I th q e to the minus I th, and I thought you'd get a coffee.
That's the rest.
Okay. So this is the position operator in quantum mechanics at time t, and this, of course, is the position operator in time 0. Now, as a slight diversion, I'd like to show you something. Suppose we have some state at time 0, and we have q of t state at time 0. So we'd agree that this would be the mean value of the position operator at time t. Now you see what this is. This is psi of 0 e to the I th q of 0 e to the minus I th psi of 0. Okay. Now, unfortunately, we have to do the risky thing of actually thinking. And if we think, what we see is, what time will this be if we're going to get the right answer? Well, what's the thing here? The thing here is, let's imagine that t is positive. Then the time here is ahead of the time there by t. So here, the time has to be behind by t. So this is actually minus t, minus t. Okay? That means that all these years people have been lying to us. In other words, the sense in which we say that psi of t is this is only the sense in which that state, the mean value in that state of the operator at time 0 gives us the mean value of the position operator at time t. So in fact, e to the minus I th on psi 0 actually gives us the state at minus t. Yes?
Isn't that the same under time reversal?
Oh God, time reversal is so spooky, I don't even want to think about it. You know, time reversal is an anti-unitary, anti-linear transformation. All right. Now, how anything this simple could be that, I don't know. But in any event, you get a candle, I guess you remember. Any other questions? All right. So this is why various times I've mentioned this. It's also, if I remember correctly, I never quite understood this, but Schwinger would often, when he was teaching quantum mechanics, would often say something very much like this, not in a long-winded way the way I have, but when he'd write down a time-dependent Schrodinger equation, he always seemed to intimate that that we should keep this in mind and not be fooled. But anyway, This doesn't mean that the equations in the book are wrong. It just, in the book, the standard book's wrong. It just means that often the interpretation isn't quite right. And also, when you want to talk about the Poincare group, it's good to know that this thing, that this operator translates you backwards in time, not forwards, which is what maybe you meant by time reversal. I mean, that would be a much simpler notion of time reversal. I want to stay away from time reversal. That's too spooky for words. All right. Let me define Q. I shouldn't have written that big T yet. Let me define. My goodness, London fog here. This is the Minkowski space Q of t. The Euclidean Q of t is e to the th q, e to the minus th. And when we say t, we're really thinking beta, okay? So it's really an inverse temperature when we talk about this. And now we can think about a Euclidean time-ordered product, T1, T2. So what is this? And of course, this is theta of T1 minus T2 times QE, T1, QE, T2, plus theta of T2 minus T1, QE, T2, QE, T1. I mean, it's exactly what you think, where theta, of course, is the heaviside function that's heavy on one side. Okay. Now, we can imagine taking the mean value of this, or not the mean value, the matrix element of this operator in a state that is Q at time t and Q at time minus t. And so what we would have, and actually what I mean by this is just Q sub t. So this is, in fact, I could have said Q prime. In fact, it might be better to say Q prime. So maybe I will say Q prime. So I want to have e to the minus th QE of T1, QE of T2, e to the minus TH, and then let us say, well, if I call this Q prime, I'll call that Q. So let's consider this. This is, what is this? This is the time-ordered product, Euclidean time-ordered product, for the case T1 later than T2, sandwiched between two e to the minus THs. And we can now insert lots of complete sets of dyadics of QQ and PP and do all the path integrals. And in fact, before I do that, let me do this. Let me rewrite this as Q double prime e to the minus T1, because I'm going to use for QE of T1 this expression, e to the T1 T Q of 0, say, e to the minus T1T. I'm going to substitute that for this one and this one. And then what we get is Q e to the minus T1 minus T2H Q e to the minus T plus T2 H and then Q prime. So I'm taking the Euclidean time-ordered product for the case T1 later than T2 using the definition of Euclidean time dependence and then sandwich it between two, or taking the matrix element in two states, double prime and Q prime. And now then, if we actually do that, what will happen? Well, we'll be inserting these complete sets of states, and this will turn into a path integral, and it will be equal to, so let me just write it like this, it will be equal to, or to put it differently, this is the same thing as Q double prime e to the minus th time ordered product of QE T1, QE T2, e to the minus th Q prime. So that's this. And inserting all those complete sets of states, this will be an integral of Q of T1, Q of T2, e to the minus Euclidean action of Q going from minus T to T dq. Okay, now did I skip too many steps there? It's maybe you want to see a little more stuff in there?
The last step.
Yeah.
Yes, all right. All right. Okay, so let's just look at this. Of course, is the same as that, again for T1 later than T2. All right, so let's imagine we insert all these complete sets of states, and what happens is that we're going to be naming these complete states by where they occur horizontally, but where they occur horizontally is going to be associated with a time. So the first one will be, I guess it will be in fact minus t minus t2, the very first one. And then we'll get to this one, which will be T2. And then we'll go from T2 to T1, and then this will be T1, and then we'll go from T1 out to T. And actually, this one here is really, we're going from minus T to T2 is what I should have said here. That's what this interval here is. So, in other words, we'd be inserting all these complete sets of states, and this operator would be an eigenstate then of the particular Q at this point, and that would be the time labeled. That would be the eigenvalue would be labeled Q of T2, and it would be Q of T1 here. Is that okay, or do you want me to do more? All right. And of course, this Euclidean action here of Q T minus T, it would be an integral then from minus T to T of a half m Q dot squared plus V of Q of T prime dt prime, and this would be Q dot of T prime squared. So that's the idea. In other words, it's the same as, that's the same as 16.25. All right. So, now, if you want, I can certainly, do this in much more detail. And especially since this is a, holiday lecture with limited attendance. And you know, we yes.
I remember there was a reason you chose that form of the action. I mean, couldn't you have something other than q dot squared? But,
Oh, all right.
There was a reason you didn't want it, right?
That question has been very much on my mind for a couple of years now. It turns out, well, because here we're in Euclidean space, but, you know, virtually all the quantum mechanical systems we talk about, Lagrangian is 1/2 mv squared minus some potential in mechanics. And then you might say, well, this is just ordinary non-relativistic mechanics. Well, the Lagrangian for a scalar field is 1/2 phi dot squared minus a half grad squared minus some potential term. It always comes in quadratic in the time derivative. The exception is then for fermions, which is a whole other kettle of fish, so to speak. But and the situation is, if you don't have the Lagrangian q dot squared plus something else, you have a heck of a time finding what the Hamiltonian is, and it's very hard to do any of this integration. In other words, you put in a course. In other words, the steps that I've left out here is you insert all these p states and q states, right, remember? And then you wind up, you want to integrate over the p states. Well, you can do that if p occurs quadratically in the Hamiltonian. If it doesn't, you don't have a Gaussian integral and you don't quite know what to do. And the problem is that also let me put it this way, it's not well known how to do that in general, even on a lattice. Because what you don't have, you see, in this system here, you always get to something that is e to the minus something, you know, bounded below or more typically positive. So that thing damps everything. This term damps everything. If you can't integrate over p, then you get something that's an integral over p and q, e to the I q dot minus h. And so you've got a complex path integral over p and q. And it's just, there are no settled ways for doing those things. I actually thought I had good ways, but it turned out that although mathematically the formula was correct and exact, it was only correct and exact if you did the integrals exactly, not if you Monte Carlo the integrals. And all right, now let's see. I'm going to turn around and I want somebody to, I want to vote, okay? I don't want to look at the people. I'll just close my eyes. All right. If you want to see more detail on this derivation, in other words, I still left out a lot of steps. I can put them all in. If you want to see them, raise your hand, and then somebody tell me how many hands are up. How many hands? 0? One. All right. If we can get to 2, I'll put in all the steps.
You have 2 hands.
All right. He has 2 hands. All right. All right. So I'll have to put. This is my left arm is going to be down now. So this is going to be. Okay, so what do we have? We have q double prime, and we'll e to the minus t minus t1. Oh, listen, h here. Yeah, well. And q Okay, so what we want to do is we want to deal with this. Well, what we do is we rewrite this as a product of a zillion of these things, e to the minus epsilon h, and how many of them? There would be t minus t1 over epsilon. That would be the number of them. And then a q, and then a product of e to the minus epsilon h, and we'd have t1 minus tt over epsilon of those. A q, e to the minus t plus t2 over epsilon. What am I saying here? All right, hold it, I just went off the rails. It's product t plus t2 over epsilon, that's the number of them, e to the minus epsilon h q prime. Okay. Now each h, of course, is a half p squared, or is p squared over 2m plus v. And so each of these guys is e to the minus epsilon p squared over 2m, e to the minus epsilon v, e to the minus epsilon p squared over 2m, e to the minus epsilon v, epsilon p squared over 2m. Okay, so and if epsilon is sufficiently small, then this more or less is true. And now we insert complete sets of q states on each, here, and complete sets of p states there. And the same thing here, the p states, and here, q states, and so forth. And so now we have a zillion integrals over p and q. But the p's, of course, the p states are eigenstates of p, the q states are eigenstates of v of q, or q in v of q, and then there is the inner product of these states is e to the I p times one q minus the other q, and we rewrite that as epsilon q dot. And then we do all the integrals over all the p's, and because p is Gaussian, we can do those integrals. And so what we get then is, let us say, q double prime, product, again, t minus t1 over epsilon. And now this thing is e to the minus q dot squared, it's actually m over 2, q dot squared minus times epsilon minus epsilon v of q. And in each case, in this product, it's a different q, and we label the q's by, there are t minus t1 over epsilon q's here, and we label each one by an appropriate time. And then there's a q, and so this guy inherits the time. Well, it turns out that the time there is t1 because of the ordering. And so this one we call this q of t1. Then the same thing here, and this one is q of t2. And then this is a product of e to the minus m over 2 epsilon q dot squared minus epsilon v. And the same thing here, minus m over 2 epsilon q dot squared minus epsilon v, and then finally a q prime, or equivalently, we integrate. So this then is a path integral dq, and it's then e to the minus, then we add up all these exponentials, and it's an integral from minus t to t of a half m q dot squared plus v of q dt prime. And then down here we have two factors left over, q1 and v q of t1, whoops, that's a t. Q of t1 and q of t2. Okay, so I hope that's okay. So now, on the other hand, if we just took the matrix element, let us say q double prime e to the minus 2th q prime, well, this would be an integral e to the minus the same se dq, but there wouldn't be any q's down here. And of course, all of these integrals here go from q prime to q double prime. Okay, so now suppose we take the ratio of these things. Then we've got q double prime e to the minus th time ordered product of q of t1, q of t2. And of course, if we had the other time, then there would be, this would be t2, this would be t2, this would be t1, and so forth, and just 1 and 2 would be interchanged. And so the right-hand side would be essentially the same. And we would have here e to the minus th q prime, and I want to take the ratio of that to q double prime e to the minus 2th q prime. Well, we see this would then be a ratio of two path integrals. One is q of t1, q of t2, e to the minus this se dq, and then it would be divided by e to the minus se dq, where se is this integral from minus t to plus t of this quantity here. Okay? All right, now what happens here is we take the limit t goes to infinity. Well, that projects out the ground state. And so what we can say, in fact, is e to the minus th q prime is e to the minus te0 0 0 q prime. Okay? And on the other side, q double prime, and I'm taking the limit t goes to infinity, e to the minus th goes to e to the minus te0 q double prime 0 0. So this left-hand side in the limit, what do we get? Well, let me just act here. This thing turns into 0 0 q prime e to the minus te0, and then down here the same thing happens. In fact, this whole thing turns into e to the minus 2e0t q double prime 0 0 q prime, And then up here, this thing turns into okay. So you see you have in the numerator two factors of e to the minus TE0 and 2 in the denominator. You also have this guy and that guy, and this guy and that guy. And we have an integration. And let us, in fact, keep Q prime and Q double prime fixed. Then they completely cancel. And when they completely cancel, then we've just got the right-hand side. And what I'm a little bit concerned about is that on the right-hand side, we're still going from Q prime to Q double prime, whereas all reference to Q prime and Q double prime cancels. If Q prime and Q double prime are fixed here, they just cancel. Well, what certainly will work is just to say that we're going to integrate over Q prime and Q double prime in numerator and denominator, and then that's what we get here. And in fact, normally we think of this thing as an integral over just all paths, and it's weighted this way. Okay. So going to a more general situation, what we have is 0 time-ordered product of Q of T1. These are all Euclidean, so it's Q Euclidean Tn is then right, you notice when these things cancel, there's nothing left but the mean value in the vacuum of the time-ordered product. And then on the right-hand side, what we have is an integral Q of T1 dot 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 Q of Tn e to the minus S of Q dQ, and then we still have to divide by e to the minus S of Q dQ. And this S of Q is Euclidean, meaning it's kinetic energy plus potential energy. And so it's basically e to the minus energy, although it's more properly called Euclidean action. Okay. So notice we have the time-ordered product symbol still on the left, but on the right, all we have are these different T's. So in other words, this single ratio of path integrals gives us the time-ordered product for whatever the correct order is, because the order of time was enforced by just the order in which we inserted the complete sets of states. Okay. All right, now let's jump to finite temperature field theory. And as you know, the jump from quantum mechanics to field theory is, well, we can take this in 2 steps. We can say we have a bunch of Q's, independent quantum variables, and Qi dk is I h bar delta ik, and then of course pi k is 0. All right. And we jump from that then to imagining that I labels a point in space, not space-time, just space, and then, and we call that space x, so it's as if we said q sub x, q sub x prime, that should be 0, but we're going to call these fields phi of x, phi of x prime, 0, and then the p's we're going to call pi of x prime, 0. And now what we're going to say is that phi of x, pi of y is I delta cube of x minus y. So this is the theory defined all at one time, say time 0 all over space. And then the way we move forward or backwards in time is by using the Hamiltonian. And I'm going to assume we have one of these nice Hamiltonians, which is a half pi of x squared plus a half grad phi squared plus a mass term, and then some p of phi, which is the interaction d cubed x. Okay. So that's the Hamiltonian. As I said, this is sort of the most general Hamiltonian that actually doesn't get us into serious trouble. Now, once again, and when we go to the path integral, we know we're going to have eigenstates of phi and pi, and the eigenstates of phi are going to be eigenstates of all of this. So I'm going to rewrite this as v. So I'm going to say that this is actually an integral of 1/2 pi squared of x plus v of x, d cubed x. And v will be an eigenstate of, it'll be a function just of phi. Okay. Now, the analog of the q and p states in field theory, you know a lot of this, is, and I'm going to introduce this time label. This would be phi prime of x. And we can also have eigenstates of pi, again at time 0, and I can call them pi prime, and that would be pi prime of x. So we have eigenstates of phi and pi, just like the eigenstates of q and p in quantum mechanics. You should be cautious about these, though. Remember, in quantum mechanics, eigenstates of q typically have infinite energy. Why? Because if you think of them as a Fourier transform, they're an integral of a linear combination. In other words, I should just write it. Q can be thought, Q prime can be thought of as an integral e to the, all right, let's just insert the p states. Well, I don't have any eraser, hold on. This thing is a phase factor, so this is e to the minus I, q prime p, p, dp. So you see this has components with arbitrary high momentum, no damping, just an extra phase. And so these are typically infinite energy states. And The p prime states, on the other hand, for the Hamiltonians that we normally consider in quantum mechanics, those are of finite energy. In fact, the energy is just basically p squared over 2n, if p is the eigenvalue. In field theory also, these states tend to have infinite energy, and the phi states, because of this pi here, because let me take the inner product of these states. So a phi prime is a phi prime with an integral of some fudge factor f. Not an integral, it's an exponential. E to the I integral phi prime of x, pi prime of x, d cubed x. So in other words, the inner product is a phase factor, as in quantum mechanics, but the phase is an integral. And then there's an overall factor. And that factor will typically cancels in most cases. And so if we think of computing something like this, e to the minus epsilon h phi prime, so then this would be what? It would be phi double prime e to the minus epsilon over 2 integral pi squared d cubed x pi prime e to the minus epsilon integral v of phi of x d cubed x, and then phi prime on the right. And we'd have to be integrating d pi prime. So we'd have to be integrating over all of the pi's to make the identity operator here. And this is an eigenstate of that. This is an eigenstate of that. And the inner product of these two, well, it's they're phase factors like that. And so what we get is absolute value of f squared e to the minus epsilon integral v of phi prime of x d cubed x, and then an integral e to the minus a half epsilon pi prime squared of x plus I pi prime of x, and now phi double prime of x minus phi prime of x d cubed x. That's all in the exponent, and then d pi prime. Well, this is our Gaussian integral again, and we imagine you can imagine space on a lattice, and you just do the pi integration separately at each point of the lattice. And we then pull this notational stunt. Namely, we say that epsilon phi dot prime of x is phi double prime of x minus phi prime of x. So we associate that jump with an epsilon phi dot prime, and then this thing is some other factor which I called f prime, e to the minus epsilon integral 1/2 phi prime dot squared of x plus v of phi prime of x. Oh, that's a prime. Okay. Phi prime of x d cubed x. Okay. So that's this matrix element. So to repeat, the matrix element between two eigenstates of the field operator are some fudge factor times e to the minus epsilon, a space integral of 1/2 phi prime dot squared plus v d cubed x. And of course this is the Euclidean action density, and epsilon is a dt. If we put together an infinite number of them, then what we would have would be, say, phi sub beta e to the minus beta h phi sub 0. This would be an integral from fields phi 0 to phi of beta e to the minus integral 0 to beta d, what do I call it, t integral d cubed x, all space, and then it would be a half phi dot squared plus b of phi. Okay, that's that. Right, and then d phi is all the pi integrations are going. So that would be our path integral. And if we then expanded everything, we'd say, well, we have a path integral d phi, e to the minus, and now this would be an integral, let us say, d fourth x, but only in time up to beta. So I'll say 0 beta here. And it would be a half phi dot squared plus a half grad phi squared plus a half m squared phi squared plus some p of phi. So that's the path integral formula in Euclidean space for a field theory at temperature beta, inverse temperature beta, say. And if by an abuse of language we call it, well, let's see, what should I call this? I call it h of phi in the book, and it's an energy density, but it's more properly called the Euclidean action density. Classically, it's effectively the same thing. So, as I said in the book, I call this H. All right, any questions about this? All right, well, the next step is to think about the partition function. And of course, the partition function, as you know, is z of beta, and this is the trace. It's trace. Trace. E to the minus beta h. By the way, when I was a first-year graduate student, I had to skip one of Schwinger's lectures, and when I got back, I saw all these things that looked like this. And I said, oh, he's introduced H-bar. No, it was a trace. So it was a while before I caught on during that lecture. All right. So that's the partition function, and this would be what? Well, it would be an integral over all fields that go, in other words, we would set phi beta equal to phi 0, and we'd integrate over all of them. So that then is the integral over all periodic fields, so to speak, d phi e to the minus integral, let it just say L e equal to this. That's probably the best way of doing it. Now, just as position operators have Euclidean time dependence, so of course fields do too, and the Euclidean field at x and Euclidean time t is just e to the th, phi of x and 0 to the minus th. And of course the Euclidean time-ordered product of two fields is defined in the obvious way. We use the Heaviside function, and so it's basically time-ordered product of phi e x 1 T1 phi E x2 T2 h theta of T1 minus T2 times phi E, let us just say phi E1 phi E2 plus of course theta of T2 minus T1 phi E2 phi E1. And well, of course the part that I skipped is the essential part, namely that this is theta of T1 minus T2, and it's e to the T1H phi E of simply x1 e to the minus T1 minus T2H phi E of x2 e to the minus T2H, and then plus theta of T2 minus T1 e to the T2H phi E of x2 e to the minus T2 minus T1 H phi E of x1 e to the minus T1 H. And so basically you're going here you're going from T1 to T2, and then from T2 out, and so the next thing is to sandwich these between e to the minus TH and let T go to infinity. And moreover, what we have here is e to the minus beta h. We can think of that as the density operator. Rho is e to the minus beta h divided by z of beta. So that makes the thing have unit trace. The trace of rho is 1, and rho is obviously Hermitian, and positive and so forth. Okay, so what is the mean value of the time-ordered product then in this density operator? So the mean value of the time-ordered product of phi E of x1, phi E of x2, mean value, well, that would be the trace of rho, the time-ordered product, phi E, let's just say phi E1, phi E2. It would be the trace of this, and that then would be the trace of e to the minus beta h t of phi E1, phi E2, divided by the trace of e to the minus beta h, because that's the normalization here. And now if we express everything in terms of path integrals, what we have in the numerator is an integral phi of x1, phi of x2, e to the minus Euclidean action d phi, and then in the denominator, this thing gives us e to the minus Euclidean action d phi. So we get a ratio of path integrals, and the only restriction is that all of these paths go from one field to the same field at a Euclidean time beta later. So we're integrating over fields that go from phi of 0 equal to phi of beta, and do anything in between, and then we integrate over all phi zeros. Okay. So it's basically periodic in time boundary conditions. In the zero temperature limit, this thing projects out the vacuum, and what we have then is the formula ground state time ordered product phi e, let me just say 1 dot 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 phi e n. Ground state is integral phi 1 phi n e to the minus Euclidean action d phi divided by, whoops, e to the minus Euclidean action d phi. Okay. So that's the ratio formula. So these things, in other words, that we want to compute, they turn out always, or at least almost always, to be ratios of path integrals. And so these various things that are hard to define, what actually d phi is, in other words, if we put the thing on a lattice, we have a fudge factor raised to some absurdly high power, but the same fudge factor as occurs in the denominator, to the same power. And so that cancels. Any questions? All right. Well, the next thing is to repeat everything I've said, not Euclidean time, but ordinary time. So we sort of have two time zones in the physics department, real time and Euclidean time. All right, so here, what we're talking about then is phi double prime e to the minus I epsilon h phi prime. Well, this thing would be, of course, integral phi double prime e to the minus I epsilon integral pi squared over 2 d cubed x. The pi states pi prime e to the minus I integral v d cubed x, and then phi prime. So this is an eigenstate of that, this is an eigenstate of that, and what we wind up with is some fudge factor f or actually some f squared e to the minus I epsilon v d cubed x prime, and then, or d cubed x is the way I wrote it, and then an integral e to the minus I epsilon pi prime squared over 2 plus I pi prime phi prime dot d cubed x d phi prime. So once again, the inner product of phi double prime with pi prime and a pi prime with phi prime gives us two phase factors that we write as e to the I, let's see, there's an epsilon that I want, e to the I epsilon, e to the I epsilon phi dot prime, and e to the I pi prime. Okay, so that's phi dot prime, epsilon, and so forth. Now we do the d pi prime integration, and that gives us the usual action. All right, I see a frown. This is e to the minus I epsilon pi prime squared over 2 plus I pi prime phi dot prime epsilon d cubed x, all in the exponent. Okay, vocalize the question and then I'll try to answer it.
No, me?
Yeah.
Oh, well, then that second term has epsilon squared. is that first epsilon? I mean, everything's in the,
Everything's linear in epsilon. The epsilon comes out here because we do this notation that epsilon phi dot is phi double prime minus phi prime. And so the thing is linear in epsilon, it's a Gaussian in pi prime, and we do the pi prime integration. All right, let me go to the front and see if we can see what this says. Let's see, we've got 15 minutes left. Maybe I should actually erase one of these boards correctly. Because what I'm erasing now is probably what I'll need to refer to in a moment. Maybe I'll erase them. Okay. What we have then is that the amplitude, so let me just see what, I've now lost track to some extent of how far we've gotten. Yeah, I guess what I just derived was that the amplitude for just going, let's just say the matrix elements of e to the minus I epsilon h is what I just derived. Now, of course, we can string a bunch of them together, and when we do, just as in the case of coordinates, we get a full path integral. So, in other words, what we get then is phi double prime e to the minus 2I th phi prime. I'm going to let t get big in a moment. This would be then some integral e to the I integral a half phi prime dot squared minus v of phi d4 x, where d cubed x is over all space and the dt goes from, let us say, minus t to plus t for a total interval of 2t. And we're in the real time zone as opposed to the imaginary time zone. And what we of course do also is we path integrate over phi. And we path integrate from over all fields that go from phi prime to phi double prime in time 2t. Okay. And this thing here, of course, is the ordinary Minkowski action. And so we have this, that this thing is equal to a path integral e to the is d phi. And the only reference to the final and initial states are that the fields we are integrating over are phi prime at time minus t and phi double prime at time plus t. Okay. Well, as you know, the Heisenberg field phi of x and t in the real-time zone is e to the I th phi of x 0 e to the minus I th. And, well, once again, the time-ordered product, you know what the time-ordered product is. So I'm not going to write that down yet again. But what we can do is imagine the time-ordered product for t1 greater than t2, sandwich it between e to the minus I th, time-ordered product phi of x1, phi of x2, e to the minus I th. And so this is then e to the minus I t minus t1 h phi of x1 and 0 e to the minus I t1 minus t2 h phi of x2 0 e to the minus I t plus t2 h. Okay, so that's what the time-ordered product looks like stuck between two phase factors. Okay, and so what we're doing here then is if we forgot about the fields, we'd have a product of time evolution operators that would just be e to the minus 2ith. Because you'd have e to the minus ith, the t2 terms would cancel, the t1 terms would cancel, and then we'd have e to the minus I th here. Okay. And so we can now take the matrix element of this between, let us say, phi prime here and phi double prime there. And so this would be phi double prime here and phi prime there. And now we insert these complete sets of states, phi states and pi states, you know, infinitely many of them here. Okay? And what do we get? What we get is phi double prime e to the minus I th t of phi x1, phi x2, e to the minus I th phi prime. We get that this is an integral phi x1, phi x2, e to the I s of phi, d phi, and the only restriction is that the phi's go from phi prime to phi double prime as time goes, real time goes from minus t to plus t. And, okay. Now, obviously the same thing works if we had n fields here, we just have n fields there. So it's a very nice, these path integrals are just ideally suited to time-ordered products in one time zone or in both time zones. Time-ordered products of fields get naturally expressed in terms of ratios of path integrals. Again, as long as we're dealing with theories that are of the conventional form. And it turns out that all the theories of the standard model, one way or another, you can do this. Okay. All right, well, as I said earlier, these states phi are eigenstates of typically infinite energy, in fact, really infinite energy. I mean, if the ones in quantum mechanics were eigenstates of infinite energy, these guys are much worse. You don't even want to think about how infinite the energy is associated with that. So what we want to do is get down to the ground state, and so we have something like this. 0, 0, ground state, phi double prime, e to the minus 2ith, phi prime, ground state, and now what do we have? I'm going to integrate d phi prime, d phi double prime. So I'm doing something, I don't have any field operators, I just have the Hamiltonian. And so in other words, it's the thing that would go in the denominator here. And what is this? Well, let me make sure I've got it. Well, integrating over the fields just gives us the identity operator, and so this is the ground state. The ground state's an eigenstate of the Hamiltonian, eigenvalue E0. And so this thing is actually equal to e to the minus 2it E0. And that's actually exact. Okay. Because the integrations over phi and pi, these are phi and pi at one time, because they're just these eigenstates. And then at this time, so two different times, effectively. We integrate over all the fields, we get two identity operators, and then we just have the mean value in the vacuum of e to the minus 2ith. And if E0 is the eigenvalue, is the energy of the vacuum, that's what you get. By the way, this E0 is presumably the volume of space times the energy density of the vacuum, and the energy density of the vacuum presumably is a small positive number that's been measured to be dark energy. That's my view. It's also a common view, actually, among a certain fraction of the population. Okay. On the other hand, we know that this thing is our standard path integral. So this thing is actually an integral 0 phi double prime e to the I s of phi d phi. Well, I should have. Let me stick this phi prime 0 there. D phi prime, d phi double prime. So now on the right-hand side, we've got an integral over basically just all fields that go from whatever at minus t to whatever at plus t. The whole shebang is on the right-hand side, and this is on the left-hand side. And now we can do the same thing for this. In other words, we take a phi double prime and a 0, a phi double prime and a 0. In other words, well, we have almost no time, and I have almost no space, so what we get is e to the minus 2I t E0, 0 time ordered product, 1 dot 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 n. Let me just, to save time, write it this way. This then is an integral 0 phi double prime phi 1 dot 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 phi n e to the I s of phi, and now phi prime 0, and now we have d phi prime, d phi double prime. And okay, what does the right-hand side say? The right-hand side says you just integrate over all possible fields that go from minus t to something or other at minus t to something else at plus t. You weight them with the classical action, and okay. So what do we have? We have these same factors first of all, all right, so we take the ratio of the two. Taking the ratio of the two, we have e to the minus 2I TE0 over there, and over here, the other thing is integral 0 phi double prime e to the I s of phi, phi prime 0 d phi d phi prime d phi double prime. So this phase factor obviously cancels. So the time-ordered product in the real-time zone of n fields is a ratio of two path integrals, and in these path integrals, what we've got is we've got these matrix elements here and there, and we integrate over everything. All right. And these guys effectively produce the I epsilon in the Feynman propagator when we do perturbation theory. Otherwise, if we don't, I don't know, I want to cancel them, but I'm not quite sure I can do that. All right. Okay, so any questions? All right, I guess we can end it.